Hi, this is Jeff Spence, your Math 120 instructor for the Community College of Denver. And this is our video lecture over section 11.2, which covers our second counting technique called permutations. So we're going to use the fundamental counting principle to count permutations. That'll be our first example. The fundamental counting principle is what we learned in the first section, 11.1. The fundamental counting principle essentially tells us that we can multiply our options at each stage to figure if we're going to select one thing from each group. We can multiply our number of options in each group to get our total number of options at the end. Second objective is we'll evaluate factorial expressions, which will help us understand and use the permutation formula. And then we're going to do some examples with permutations. So, permutation. Big thing with permutation is an ordered arrangement of items. That occurs when no item is used more than once. So that's a key thing. You cannot select anything again. And the order of the arrangement makes a difference. Okay, so the order matters is what I say. So let's say you need to arrange 7 of your favorite books along a small shelf. How many different ways can you arrange the books from left to right, assuming that the order of the books makes a difference to you? So the big thing here is, like, when order matters, we can look up things of like first through second, through third, through fourth, that the order matters, like if we're talking about picking winners of a race or a prize or something like that. Or in here, when we're talking about arranging the books, we're looking at things from left to right. Okay, so it says 7 of our favorite books along a small shelf. How many different ways can you arrange the books? Well, we can choose any of the 7 books for the first position on the shelf, so that's why this 7 is here. So this is the multiplication principle to attack this problem. This leaves 6 choices for the second position because we put 1 book here. Now we have 6 choices for the second position, 5 choices for the third, 4 for the fourth, 3 for the fifth, 2 for the sixth, and 1 for the seventh because we keep using 1 book. And we're not going to reuse any of the books because we're putting them in order. So from left to right, when you multiply like this, left to right matters, or arrangement matters. There's 5,040 different ways we can arrange our 7 books on a shelf from left to right. Now, they want to get into factorial notation just to explain something about the formula that's coming up. So 7 times 6 times 5 times 4 times 3 times 2 times 1 is called 7 factorial and is written 7 with an exclamation point at the end. So anytime you see a number factorial, it really just means to multiply by the descending integers all the way down to 1. So, for instance, if you had to do like 8 factorial over 5 factorial, this means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. But they stopped at 5 and wrote the factorial because when you divide by 5 factorial, these are just going to cancel. The 5 factorial, even though it's 5 times 4 times 3 times 2 times 1, they cancel each other because they're the same. So we're left with just 8 times 7 times 6, which is 336. Same example here for the formula. This is a preview for the formula. So the permutation formula is, if we're selecting our items from n items, so we're selecting our things from a total of n things. So n is the whole group. That's the number of options that we have. It's a big. Sometimes I call it the bank of items. That's our total number of items, and we're going to select a certain number from that. Then we can use the permutation formula when order matters. Now remember, when we're selecting these things from the bank of things, if we're using the permutation formula, just like this says, you cannot pick any item more than once, and the order makes a difference. So here's the formula: n factorial over n minus r factorial, in parentheses, n minus r. So I'll show you on the calculator here when we get to example how you can just use this formula without actually having to do the math of the factorials. But if you're comfortable with the factorials, you should use them. So it says you and 19 of your friends have decided to form a business. The group needs to choose 3 officers, a CEO, an operating manager, and a treasurer. How many ways can these offices be filled? Well, we're selecting 3 positions, CEO, operating manager, and treasurer, from a bank of 20 people, because it says you and 19 of your friends. So I believe we're talking about 20 people that we're selecting from. So we have a group that we're selecting from, and we're selecting 3 positions. And the positions are different. Okay, so the CEO does something different than the operating manager, which does something different from the treasurer. So the order in which we select these matters. It says how many ways can these offices be filled? So they're explaining we're selecting 3 things from a bank of 20 things, and the order matters because each officer has a different responsibility. So that means that we're going to do 20 permute 3. 20 permute 3 is 20 factorial divided by 20 minus 3 factorial using the formula from before. So that's 20 factorial over 17 factorial, which means we can take the 20 times 19 times 18, stop at 17 and cancel that with the denominator. So we just have 20 times 19 times 18, 6840. However, let me show you this with the calculator. So if I want to do this function on the calculator, start with the number 20, go to the math button, go over to PRB, and find the NPR function. Then you press 3, and it will do all this math for you and get 6840. And it's totally okay if you want to use the calculator to do this problem in this way. If you're worried, if the factorial notation and this cancellation stuff is confusing you, it's totally okay to use this formula. Now, if you have a different calculator, TI-30X2S, you should be able to find a probability button or a second key that gets you to a PRB. So I know to get through it on the graphing calculator, you get to the PRB menu by pressing math and going over. But the TI-30X2S's or some other calculators should have the PRB button or a second key that gets you to this NPR function. And if you can't find it, just Google it about your calculator, how to get to the permutation formula, and it should describe it pretty easily. But you always, if you're using this formula, you have to type the number, the n first, then the formula, then the last number, and it'll do the math for you. Now, why does order matter when we're selecting these things? So let's say the 3 people that we're going to select for these positions, their names are Tom, Bob, and Heather. Tom, Bob, and Heather. Okay, so if I choose Tom for the CEO, Bob for the operating manager, and Heather for the treasurer, that's very different than if I select Heather for the CEO, Tom for the operating manager, and Bob for the treasurer. Notice how those are 2 very different ways to select them. So the person I select first to be the CEO, it's different. Whoever I select does a different thing. So if you mix the names and it requires different responsibilities, then order definitely matters here. Okay, so let me give one more example. So another example that we'll see here is if you make like a password or combination, where it's like a sequence of numbers to access something or letters. So here's an example. It says, how many 4-letter passwords can you make if you cannot repeat a letter? So this is a permutation problem. First, because we're not repeating any of the selections of the letters, and order matters on a password. Okay, from left to right, the order matters. If your password is ABCD, that's very different than a DCAB password. Okay, so passwords, order matters. And since what's the bank of things that we're selecting from? 26 letters, and we're picking 4 of them without repetition, where order matters. So 26 permute 4. Let's type that in here. Oh, come on. Is we start with 26, get the permute function, select 4, press enter. There are 358,800 different passwords, 358,800 passwords that we could make if we do not repeat a letter. Now if you look at this next problem, it says how many 4-letter passwords can you make if you can repeat a letter? Now if you can repeat a letter, then this goes back to the multiplication principle that we learned in 11.1. So this is really just a password. You have 26 different letters that you could pick for the first letter. You have 26 different letters that you could pick for the next letter. So I'm just multiplying 26 times 26 times 26 4 times. I have 4 stages of choices because it's a 4-letter password, and I have 26 options at each stage. So if I take 26 times itself 4 times, that's just the same as 26 to the 4th. I have 456,976 different passwords that I can make. 976. Okay, so notice the difference. With permutations, we never repeat, but order matters. In the multiplication principle, you can kind of thinking of it as order matters because you're doing your first selection, second selection, third selection, and fourth selection, but you can repeat. So generally, if you can repeat selections, you want to use the multiplication principle. We'll continue this discussion with combinations in 11.3 and compare combinations and permutations at the end. We'll see you then. Good luck.